There's a lot of reduction and a lot of oxidation in this chapter. So that's their two primary focuses as far as the chemistry goes. And all of it within the context of synthesis. So one of the first reduction things that pops up is the Wolff-Kishner reduction, or Kishner, I keep calling it Kitch, which you've already seen. Right? We talked about that when we looked at chapter 18. That's looking at nitrogen as a nucleophile. Right? So hopefully you guys at least vaguely remember that your nitrogen acted as a nucleophile, did a bunch of nucleophilic addition, eventually ended up kicking it out, and we end up with that structure. Vaguely sound familiar? Look familiar? With the strong base, that base can then go through and start pulling hydrogens off of that last nitrogen. Those electrons shift down into the structure, which picks up hydrogen from our water. And eventually we end up doing a full reduction where we release nitrogen gas. The formation of the nitrogen gas is the big driving force for this reaction. Okay? Nitrogen gas being incredibly stable, bubbles out of the reaction, we can't reverse it, everything's fantastic. Okay? So it's kind of a neat reaction in that we can completely remove the carbonyl. Okay? So we can go all the way down to an alkane as opposed to, say, stopping at the alcohol if we had used what reagent? Vidig would take you to an alkene, not down to an alcohol. Grignard would do it. But Grignard also changes the carbon structure. How could we reduce it without changing the carbon structure? Base isn't going to work. That'll end up giving us an enolate, which could potentially do some other stuff. All I'm saying is we want to take it to an alcohol. LDA is a base. So let's do a quick modification of our structure. If I wanted to take this down just to an alcohol, I don't know why I did it that way, but I did. A hydrogen nucleophile, there's only two sources that we're aware of for hydrogen nucleophiles. LiAlH, or LAH as it's sometimes abbreviated, lithium aluminum hydride, and the other one? NaBH4, sodium borohydride. Right? Those are our two hydride nucleophiles. Right? What the book then goes through and does is look at a couple other reduction mechanisms. Okay? But before we even get into, say, the Clemenson, why might we want another type of reduction mechanism? Why is that important to have multiple different types of reduction abilities?
You're trying to make a specific product.
If trying to make a specific product isn't necessarily going to reveal it, because both reagents would go through and still do the same thing. They do a reduction. What was your suggestion, Princess? And I'll come back to you.
Some structures have different functional groups present.
Our starting material may have different functional groups present. So we could have different carbonyls. If we had different carbonyl compounds, they're going to react differently. So we may need a different reducing agent to go ahead and react with that particular carbonyl. What were you suggesting?
Kind of like that they might have certain things in the structure that also react.
Which is where I figured you were going to, but I figured he was going to say something similar. We could have a larger structure that has a bunch of different functional groups in it. If those other functional groups are sensitive to the reagents in, say, the Wolff-Kishner reaction, I'm not going to be able to run this reduction because I may end up doing some side reaction somewhere else. Okay? What might be a characteristic of some other functional group that we could add to this structure that would make the Wolff-Kishner reduction not a good idea? That was a tricky statement. Okay. An alkene isn't going to necessarily be an issue. What does the Wolff-Kishner or Kishner reaction require the presence of? Strong base. What if there's an acidic functional group somewhere in our structure? Well, the strong base could neutralize it. So having an acidic functional group could be problematic. What else? This actually is a strong base. So we just said having an acid could be something that could get in the way. What are the nitrogens acting as? If there is a second electrophile in our starting material, those nitrogens may attack that other position. If we only want them to attach or attack the carbonyl, we need to come up with some kind of selective reagent. Okay? Some of this can be limited by making sure we don't have other functional groups present. Sometimes we don't have that choice. Okay? So that's why we end up seeing a bunch of different ways to go through and do it. If we look at the Clemmensen reduction, what's going on with this one? You'll notice that you aren't given a mechanism. That's because it's a big, ugly, nasty mechanism that you don't want to understand anything about. But we can start to draw some conclusions about it, which we talked about on Wednesday. Not only do we fully reduce the carbonyl down to the alkane, what else happens? You may be going, well, I don't see anything else, because you guys are paid attention to what we've talked about in the class, and we only focus on the organic materials. What else happened?
The zinc picked
I went from zinc metal with an oxidation state of 0 to zinc plus 2. The zinc donated electrons into our carbon structure. Right? And it did that ultimately through a coordination with our oxygen, which means we can take our electrons from the zinc, dump towards the oxygen, which then puts too many electrons out there, which can pick up H+. Which is why, if you look very carefully, they've shown your HCl as red, and they've showed the hydrogens on your final structure as red, because that's where they came from. That may seem like an odd reaction. Why might that be an odd reaction? What charge are the hydrogens? Those would be H+. What charge is our carbon to begin with? Positive. We have a positive to a positive. That doesn't seem to make sense. That's because the zinc is messing with all of our understandings of chemistry. The zinc is donating electrons in, which allows the carbon to take the electrons from our oxygen. So zinc is getting us into what kind of chemistry? Hey, good call. This is that Oompa Loompa chemistry. Okay? We've switched the charge on the carbon through the course of the reaction. Okay? Why is this reaction different than the previous one? We're under acidic conditions now. So if we looked at our starting material and we had a basic functional group, that could become problematic. Right? What else is interesting to note in this case? What's that? The metals, yeah, that's a little bit different about what's going on here. The other big difference here, no nucleophile is being added. So we could have electrophilic sites somewhere else in the structure, and it's not going to react with our reagents because we don't have a nucleophile. Right? So the Clemmensen has a step above the Wolff-Kishner in that respect. Last one is the Raney-Nickel reduction. In the Raney-Nickel, you are responsible officially for that first step. Why are you responsible for that first step? What type of reaction occurred there? We might say protecting group because it kind of looks like that, but if we called it a protecting group, we would expect at the end to be able to see a carbonyl. And what happened to it? No, it's like an anti-protecting group. It's a nucleophilic addition reaction. The sulfur attacks the electrophile of our carbonyl. It gives us the thioacetal. Why do we reference it as a thioacetal and not a straight acetal? Because it's sulfur instead of oxygen, but the chemistry is still the same. So you're responsible for being able to do that mechanism. I have every belief that you can do that quickly and easily. Okay? That last step you don't have to worry about. That's involved in a fancy metal catalyst, looking at our nickel and the presence of hydrogen, shuttling electrons around between the nickel and the sulfur and the carbons to get hydrogens put onto the structure. Okay? What does this reaction have in common with the previous two? What's that? We can look at our product. It reduces all the way down to an alkane. So we now have 3 reagents. What else could we look for as a commonality? What's that? We do have a metal popping up in this.
It's semi-acetal or acetal-ish
How are we getting the acetal?
by adding,
What is the sulfur acting as? A nucleophile. This is similar to our Wolff-Kishner reduction in that we have the presence of a nucleophile. Okay, so again, one of the limitations here is that we want to avoid other sites of electrophilic character within our starting material, because that can potentially react with the sulfur. Okay. Your textbook's got the list of what's happening between all those. We did just summarize all of those end results. Okay. With all 3 cases, you're going all the way down to the alkane, which is kind of a neat little reaction. We can completely remove it from the structure. This becomes a bit obnoxious for you as students, which eventually we'll see somewhere in here, because we could get to a final structure. Oh, fine, let's just skip to it. Whoop. We could get to a final structure, say like propylbenzene, and we look at that, and all we see are alkanes and aromatics, and we say, well, that structure is not reactive. How could we possibly synthesize that? Okay. Well, one of the synthesis steps was to remove the functionality that allowed you to do all the chemistry. Okay. So you have to be careful that some of these reduction reactions can hide how the reaction occurred. Okay, so just watch out for that. We will come back and look at the synthesis in a little bit. Before we get to that, we've got our other hydrogenation reactions. We can take hydrogen gas with our metal catalyst, say platinum or palladium, and we can dump that in on pretty much any pi bond, and we can reduce it. The exam is written, so even if I die, it's okay. So, you've seen this type of reduction before. One of the things to watch out for in this case is how is that addition done? I know it's a weird statement. See what you can come up with. Any ideas? It's a syn addition. The hydrogens are added across the double bond on the same side of the double bond. Okay. Is that a problem with this product? Why not? There's no stereocenter, so we don't care about it. That does not mean all reactions or all reductions aren't going to have stereocenters. So watch out for those. They can pop up and get in the way. So there's your pretty picture of it. I should talk faster through this. We can do it with alkynes as well. Same deal. We can reduce all the way down. Okay. The issue with this catalyst is when we put in hydrogen, we stop at an alkene. Well, what's the problem with an alkene? Well, what happens if you have an alkene and a metal catalyst? It reduces to the alkane. Right? So what we're trying to now introduce partly within this chapter is how do we stop a reaction at an individual step, okay, or an individual intermediate. So if we try to do it with our alkynes, it goes all the way down. Okay. Are there other reagents that we could introduce? This is where we come up with this poisoned catalyst term. There's a couple different options on how you would see these. Number one, you'll see reference to Lindlar's catalyst. Is it there? Yes. So that is an important name and or catalyst thing to remember. Lindlar's catalyst will stop at the alkene. Okay, so we can throw an alkene in Lindlar's catalyst, lots of hydrogen, and we get an alkene. Nothing happened. Okay? We can throw an alkyne into the mix with our Lindlar's catalyst, and that will reduce down to the alkene. Okay, so we can get some different chemistries coming out of that with our Lindlar's catalyst. So you'll see Lindlar's. The other thing is this poisoned catalyst kind of term. It's not super obvious on what makes it poisoned. Most commonly what I've seen is if you see any reference to a metal, palladium, platinum, even nickel, and then something else. It's usually, in my experience, group 2 metals. So we take a group 2 metal and we mix it with either a carbonate or a sulfate. If you see any of those, that is your poison. Did I spell poison right? Yeah, look at that. Okay. Quinoline might show up as well. That kind of just depends on the reaction. It's such a large structure that more than likely it would just get written out as the name quinoline if you saw that pop up. Okay. So just something to be aware of on ways that you can see those poison catalysts. Which means if we now take our hydrogen and our Lindlar's catalyst, we end up with our alkene. What's an important note, particularly if we switch to a different catalyst, okay, just a poisoned one. Notice our group 2 metal and our sulfate. What's the common feature of both of these reductions? You only get the cis product. You get the syn addition. Okay? This is a feature of hydrogen gas. Hydrogen gas is too small. You need the metal catalyst to coordinate and grab things, which means the hydrogen must come in on the same side of the double bond, which means you get the syn addition. You don't have a choice when using hydrogen gas. Okay, but what if you want the trans product? How can you get the trans product? This is where we have to rely on a different source for our hydrogen. We'll use sodium metal and ammonia. So they'll usually reference as liquid. To get ammonia to be liquid, we have to drop to pretty cold temperatures. Usually, I think, negative 78 degrees Celsius, something like that. They may or may not reference the temperature. With this reagent combination, you can then end up with the trans product. It's the only one that will get you the trans product. Okay. If we have time and there's interest in it, we'll go back and look at that mechanism. For sure, we will look at that mechanism in the last unit of the semester, okay, when we start to look at aromatic rings, because that particular reagent will also mess with aromatic rings. Okay? Questions?
This mechanism is not in 17, 18, or
It's not in 17, 18, or 19. It is actually in chapter 25, I think it is. It's a radical mechanism. You're taking sodium metal. Characteristic of sodium metal is that it has a single electron. To show up there. Yeah. That single electron initiates a big radical cascade mess for a mechanism. It's kind of neat, but it's a mess. As far as looking at something like this within the textbook, you'll notice that they are varying different conditions, they're varying different metals, they're all using hydrogen, and they're reducing different functional groups in each of those stages. Do not worry about memorizing any of the details within that. If you have a metal and hydrogen gas, do your reduction. Okay? The one thing you do not want to reduce will be your esters. Okay? And we'll talk about those officially in the next sequence. You don't have to stress too much on that. Okay? At least not yet. So, synthesis of propylbenzene. How can we go through and do this? You guys want to try it on your own first? Yeah, sure. Okay. Try and run something along these lines. In this case, we're starting with 7 carbons, reacting it with a 2-carbon aldehyde. getting your alcohol, then using sulfuric acid and heat to get you down to the alkene, do the elimination. The last thought is trying to add hydrogen and platinum to the alkene. Not sure that will actually work now that I think about it. Why will that last step be problematic? What? It's not a lot of alkenes, but that's getting towards the right idea potentially. There's really only one alkene and one aromatic. What were you suggesting? The aromatic won't get reduced. So aromatic rings, which we haven't talked about yet, are incredibly stable, and so just do not react under normal conditions. Okay? However, there's a lot of resonance within this structure. That resonance may stabilize the alkene enough that it doesn't get reduced. Okay? I'm not positive on that, so don't quote me, but I think that is a potential possibility. So you could try and set it up where you could get the elimination to occur out the other direction. You would be doing which type of elimination? A Hoffman elimination. How do we get a Hoffman elimination? We need a sterically hindered leaving group and a sterically hindered base. We aren't going to get a very sterically hindered leaving group, so is there another way we can do it? At least within our halide mechanism, we could convert it to an amine. With the amine, we could go through that whole Hoffman, the traditional Hoffman elimination. Big god-awful mess.
Instead of having the Grignard being a 7-carbon, whatever, can you do 8 carbons? And that would eliminate the resonance.
If we run under 8 carbons, we'd actually have the OH on the end, which could help solve our problem there. We could probably convert that alcohol. We'd probably have to convert the alcohol across to a halide. How do we convert the alcohol to a halide? PBr3 is going to be your better bet, but HCl or HBr should work. Once we've got it to the halide, we can then do the elimination. There's only one choice for the elimination in that case. Okay. So other options. Whoops. I didn't want to do all that. I tossed one option out there as a Wittig reaction. We could try and do the Wittig. I think that's going to end up with the same issue with the double bond being in resonance, and that's going to be problematic. So the option that the textbook was actually having you push for is synthesizing that very last one. What'd you say? Sorry?
Like NaH to get the alpha carbon.
Which might be what you were suggesting, Karsten?
Not exactly.
Oh, okay. I might have to go back to you. If we then added something like NaH, we'd have our enolate. The enolate we could react with CH3I. Which gets us our last carbon. How do we get rid of the carbonyl? We can do any one of those 3 reactions, our Wolff-Kitchener, the Clemenson, or the Rainy nickel. Okay, and that would take us to our final product. Okay. So this is one of the things that is challenging within synthesis, which makes it kind of a beast to grade, particularly at this stage in the game, because you have a ridiculous amount of reagents at your disposal now. So you can do a ton of different ways to go through and synthesize a product, which makes it more difficult to grade, which is why fill in the blank is really nice. Is this the mechanism you were going to try and go through? Something along those lines?
Yeah, something like that.
Okay. Questions?
So, at least in the book, they go through, they didn't do the nickel one, they just used the, what is this, the N2H4?
The Wolff-Kitchener?
Yeah,
Yeah. So there are 3 possible options here that I listed. You could do A as Wolff-Kitchener, B as your Clemenson, or C as the Rainy nickel one.
oh, okay.
all three of those would have worked. Yeah. No, it's my fault. I didn't explain it clearly enough. Questions? Okay. Probably the more important section to look at would be your oxidation. How do we take our alcohols up to our carbonyls? Because once we've got the carbonyl, we've got all of this carbon-carbon bond formation chemistry that we can work with. So when we're looking at our oxidation reactions, those are going to depend on the starting alcohol. In all of these cases, what ends up happening? What changes as I move from the primary alcohol to the aldehyde? It is an oxidation reaction. Give me more. I actually don't want to get into the forming the pi bond necessarily, and we'll look at very carefully why in a little bit.
Maybe just remove the hydrogen.
Increase our oxygen bonds, right? What else do we do? Decrease our hydrogen. If we take a look at the carbon that is being oxidized in these cases, we started with 2 hydrogens. After a single oxidation, I have lost 1, and the last oxidation, I have none. Okay, so in each of these cases, we're increasing the number of oxygen bonds and we're decreasing the number of hydrogen bonds. Okay, our definition of oxidation. One of the things that helps is to broaden that definition, and instead of looking at it as increasing oxygen bonds, we can look at it as, we can reference it as decreasing hydrogen. Yes, fair enough. That was a dumb question. Still on the increasing aspect. Increasing your electronegative atom, okay, is a better definition instead of looking at oxygen. Okay. Oxygen is still more electronegative than carbon, so it still fits. But this definition is a little bit broader and allows you to apply to more chemistries. Okay. So all of these cases, you're removing a hydrogen and you're increasing the oxygen bonds, every single one of them. Okay. Why, with a tertiary alcohol, do we not see oxidation? There's no hydrogens at that carbon to remove. Okay? So really, when we're looking at our oxidations of our alcohols, we're primarily concerned about our primary alcohol and our secondary alcohol. And the parts that make those reactions even further important is that if we look at the primary alcohol, there are 2 oxidations. So you need to be able to decide which step are you moving to. Are you doing 1 oxidation? Are you doing 2 oxidations? How do you know where to stop? Same deal, and we don't run into that issue when we look at the secondary alcohol, because with the secondary alcohol, there's only 1 oxidation step. That's all we can do. We're done. Okay? So when we're talking about our oxidation for our alcohols, our primary focus is all in the primary alcohols. Why are we going to different positions? Do we do just an increase of 1 oxygen bond, or do we increase it twice? Okay. It's an important distinction to make, and the reagents allowing us to get to those stages really come in at that position. Interestingly enough, there is really only one, in quotes, reagent to memorize for oxidation. It's chromic acid. Okay? For oxidation of alcohols, that is. That is a bit misleading because chromic acid could get written as H2CrO4, K2Cr2O7 plus acid. It could get written as Jones reagent. It could get written as CrO3 in the presence of water and acid. There's a litany of ways to write chromic acid. Okay? You are responsible for knowing, unfortunately, all of them, which means if you see chromium, period, you're probably doing an oxidation reaction. Okay? So focus less on the exact compound, focus more on is there chromium. Okay? It is a very strong oxidizing agent. That said, it really tends to be selective for alcohols and not much else. Okay? Have we looked at oxidizing agents yet this semester? Yep. What were those oxidizing agents oxidizing? Alkenes. Right? And we looked at our alkenes, we had permanganate, KMNO4. That was an oxidizing agent. Right? Chromic acid versus permanganate. What's the difference in structure? Say that last part. I think I heard the last part right.
The permanganate only attacks for the alkenes, while the other.
Permanganate actually attacks all of them. Chromium only attacks your alcohols primarily. We can force it to attack alkenes, but not as bad, not as easily. The only difference between those structures is one is chromium and one is manganese. That's it. Okay. So everything about their character or their reactivity all ties back to potentially their electron configurations and how they can shift their electron cloud around. Okay. You aren't responsible for that. What you're responsible for knowing is that they are different. Permanganate does everything, including alcohols. Chromic acid does alcohols. Okay, so chromic acid is more selective. That said, if we throw chromic acid at a primary alcohol, it will oxidize, and it will go straight through the aldehyde and go directly to the carboxylic acid. We end up not isolating the carboxylic acid, or sorry, the aldehyde. All we get is the carboxylic acid. But what if you want an aldehyde? Well, then that reagent sucks. We need a better reagent. Okay? We need something that's a little bit milder, a little bit more politically correct per se. So we can look at politically correct chromic acid, also referred to as PCC, okay, for pyridinium chlorochromate. Okay, you probably like the PCC or the politically correct better. PCC will stop at the aldehyde. Right? It will still oxidize secondary alcohols. Right? So the reactivity between chromic acid and PCC is almost identical. The only thing that differs is that for some reason, PCC cannot oxidize aldehydes. Chromic acid can. That's a bit puzzling. Why that difference? We're still looking at chromic acid. Pyridinium chlorochromate. Get rid of that pyridinium and chloro, that is chromate. That's the exact same thing in chromic acid. All of a sudden, by adding this pyridinium and chloro, it seems to all of a sudden change the chemistry. Let's disappear from that for a moment, pretend you didn't see that. So we've got the pyridinium. Which is actually pyridine plus hydrochloric acid. So we still have an acid present, and then we still have our chromate. If we look at our chromic acid solution, what do we have up there? We still have our chromate. We still have an acid source. It's typically H2SO4. What else is present with chromic acid? Not so much heat.
The potassium.
Potassium isn't going to play a big role in this.
Water.
What was that?
Water.
Water. So if we now look at our comparisons, chromic acid or chromate is the same in both. We have an acid source the same in both. Our big difference sits on the difference between water and pyridine. What is the difference between water and pyridine? So we can look at size. Before we look at size, we should look at something that makes it reactive.
Say that pyridine might be a stronger nucleophile than nitrogen.
So, important point, you've noticed the nucleophilicity. Okay, so both of them have lone pair electrons that could potentially be donated into a structure. Okay. And nitrogen being less electronegative, we might expect to be a better nucleophile. But you guys were saying something down here that was a little... Before we even look at stability, maybe you're going there. Because what?
Because of how the pyridine is in the ring.
Kind of, sort of. Those electrons are now actually held pretty tight to the nitrogen. Okay? So its electronegativity actually goes up. So the difference in electronegativity between the nitrogen and the oxygen, not so different. Okay? So we can't pull to Jimmy's option. What else?
The number of lone pairs.
Number of lone pairs is irrelevant. Never, ever, ever look at the number of lone pairs. Doesn't help you. You guys had suggested something at the very, very beginning. What was your first suggestion? Size. How does that affect nucleophilicity? Steric hindrance. How does that affect nucleophilicity? Makes it less nucleophilic. Pyridine is massive. It is not a good nucleophile. Water, on the other hand, is a pretty good nucleophile. But why does that matter? If I take a look at my alcohol, do I have an electrophile? So why do I care that I have a difference in nucleophilic characteristics? Is it the alcohol that shows the difference?
No,
It's the intermediate. The intermediate aldehyde. It's that aldehyde that for some reason under chromic acid continues to react to form the carboxylic acid. It is that aldehyde under PCC that stops reacting. Why the difference? What does the aldehyde bring into our picture? Particularly at that magical position. It's an electrophile. And what can we do to an electrophile? React it with a nucleophile. Pyridine's not a nucleophile. Water is. What happens when the aldehyde reacts with water as a nucleophile? What do we form? The hydrate, right, which I will draw up here in just a second, but let's see if you can envision this. What is a primary difference between an aldehyde and a hydrate? What is the functional group in a hydrate? Alcohols. What does chromic acid do? Oxidizes alcohols. If you hydrate aldehyde, you get an alcohol, which can then react with chromic acid to add yet another oxygen bond, which gets us to the carboxylic acid. Okay. It's all based on what is effectively the solvent. By changing the solvent from a nucleophilic solvent of water to a non-nucleophilic pyridine, you've all of a sudden swapped the chemistry, and now secondary chemistry is eliminated in the case of PCC, and we stop at the aldehyde. Okay. This slide is supposed to show all of your possible ways to get, or some of your possible ways to get chromic acid. Remember I said CrO3? Okay. If you see chromium and an acid, you should be thinking oxidizing agent. Don't worry about anything else. So our big difference comes down to those two pieces. When we go through and form our aldehyde, in the case of just chromic acid, the aldehyde, do I have this nicely stepped? I do. The aldehyde reacts with water to form, after a hydrogen transfer, the hydrate. The hydrate now has a bunch of alcohols. Those alcohols can attack our chromium, potentially as a nucleophile. We end up forming our oxygen-chromium complex, which can then go through and be oxidized further down. Why does this not happen if this was, say, a secondary alcohol? After a single oxidation, what would we have? The ketone, right? Water could still potentially attack that, can it not? Yeah, perfectly valid. to go through and do that. But what's the result? A hydrate with no more oxidizable hydrogens. Which means what happens? All it does is equilibrate back to the ketone. There's no other mechanistic step it can undergo. Okay? Questions on that? Textbook has given you a partial mechanism for it. I haven't spent the time to actually look it up to validate where they're getting all their oxygens and where it's coming from. Actually, no, wait, this mechanism does agree with what I've talked about. Chromium can act potentially as a reasonable electrophile. Why would the chromium act as an electrophile? It has 4 electronegative oxygens around it. We have, in that situation, a polar pi bond, which is susceptible to nucleophilic attack. This gets us to the chromate ester. Okay. What can happen is our base, any remotely strong base like water or the pyridine, can come and remove that hydrogen, and we can do the final oxidative step, and we kick out CrO3 minus. Okay. Not super responsible for the mechanism. You're responsible for knowing what happens. Okay. Questions? Your big summary. Right? This summarizes all of the individual reactions in a very succinct fashion. It may look a bit confusing, so let's real quickly walk through it. What is happening in that top reaction? Which means I started with a primary alcohol. How do I know that? That's what our key is saying. One of those R groups is a carbon, the other 2 are hydrogens. I have a primary alcohol. How about in this one? It's a tertiary. All of those R groups end up being carbons. What's the net result? No reaction. Okay? So all this is trying to do is succinctly summarize all of those individual steps within it so that you can see what's going on. Okay? This is the part that you're responsible for. We have seen other oxidizing agents. The permanganate does the same kind of thing, and they do the same type of chemistry. Given the proper circumstances, chromic acid can be used to oxidize non-polar pi bonds, though it's not done very well or very effectively. Okay? So you have to force chromic acid to react with alkenes. What does that mean? Chromic acid is phenomenally selective for alcohols. Permanganate, on the other hand, giant mess. Okay? So we want to be careful using permanganate in an oxidation situation because it could potentially react with our alcohols or our alkenes. Permanganate is such a strong oxidizing agent, it will also go through and throw things down to the carboxylic acid. Same kind of deal. Okay? Through the same types of reactions that we've seen already when we looked at our alkenes. So the big difference, permanganate, stick to your alkenes. Okay? We can use it for the alcohols, but it's primarily used for our alkenes. Chromic acid, primarily used for our alcohols. Okay? Why would we choose one over the other? Sometimes it depends on the circumstances. Chromic acid, and in particular its byproducts, are extremely dangerous. That movie, Aaron Brockovich, is all about chromium. Okay? That was the dangerous chemical. So we tend to try to avoid using it as much as possible because we don't want to deal with the hazards of disposing of it. Okay? However, chromic acid is more selective than permanganate, so we kind of have to walk a fine line on deciding what reagent we want to use. Okay? Questions on that? Okay. Protecting groups. They introduce a whole bunch of extra terms. Labile groups. Labile just means it can come on and off. So we want to make sure that it is protected. If I want it permanently attached to the structure, I have to kind of limit its exposure. If you're following the slides, this then goes backwards in the slideshow. I just copied and pasted it to move it to the end. We've seen some protecting groups already. Our acetals, in particular our cyclic acetals, were fantastic leaving groups for which functional groups? Carbonyl. Let's switch that up a little bit more. Protecting groups for which type of carbonyls? Ketones and aldehydes. They will protect both. Okay, we can't use them as protecting groups for the other functional groups or the other carbonyl compound. So we'll come back to that. Protection of alcohols. Alcohols are acidic, nucleophilic, basic. We have all of that chemistry available to our alcohols. So if there's an alcohol in our structure that we don't want to react, we try to limit that reactivity by converting the alcohol into a non-reactive functional group very similar to alcohols, ethers. Okay. Ethers can be reversibly done. So pretty much all of our protecting groups are the process of turning our alcohol into an ether, okay, with varying reagents. The reason why we go through and form the ether is that those reactions are reversible by just adding acid and water to kind of reverse our reaction. Some of the less commonly referenced ones, DHP and TBDMSCl. DHP, this is the first time I've seen referenced ever, okay, straight out of your textbook, so there is a question in SmartWork asking about it. You're just responsible for knowing in SmartWork that, hey, you got a textbook. Take a look at the textbook. That's a protecting group for alcohols. The other one that I've seen pop up every so often is this TBDMS, tetrabutyl dimethylsilane. Okay. The chloride is to make a good leaving group. So our alcohol can attack the silicon, kick out the chlorine, and we've now protected our alcohol with this big, massively sterically hindered structure. The oxygen-silicon bond is extremely strong, okay, which then makes that bond or that structure very, very well protected. The only way that we can really break that apart is by introducing something else to force it out. We end up having to use that last reagent there. Fluoride is a really good nucleophile and can actually be used to kick out the rest of your structure. Okay. So we need very particular conditions to get our alcohol back. Okay. So this protecting group is pretty nice in that respect that very rarely are we ever going to see these conditions randomly pop up in our reaction. If we looked at our other protecting groups, to deprotect it, what do we need to add? Say even if we did the DHP? H3O+. How about the others? H3O+, H3O+, H3O+. How commonly do we see acid added to a reaction? It's pretty common. Okay. So while those protecting groups do work, we do just run into an issue with acid potentially reversing the protection. So that's why the TBDMS or our tert-butyl dimethylsilyl chloride helps us out. Okay? Oh, dang it. So that is all of chapter 19. We have that one retrosynthesis question floating out in the middle there. And then we can open it up to the floor if you guys have questions about anything in general. Do you guys want to work on the retrosynthesis on your own, or should I just kind of go through and show you what's going on with it? Just go through. Is that what it is here? So, retrosynthesis. Identify the pieces. That's 5 carbons. See, 1, 2, 3, 4, 5. So what I am doing is a new piece. Is that one. Somehow or another I have to add that piece into my structure. Before I even do that, if I take a look at that position, that carbon should be acting as a, or an, electrophile. It's our partial positive, which means the carbon of that new piece has to be nucleophile. So I might go through and just say, well, what I need to add, I can make a nice Grignard reagent. The Grignard reagent would act as a good nucleophile. My negative attacks my positive. Can follow that up with a step 2 of just H3O plus to protonate that alcohol, and I'd be all good. What is the issue with my Grignard reagent? As soon as I try to make the Grignard reagent, that negative carbon can come back and attack the electrophile within the structure. So that Grignard reagent is not going to work.
What
Okay.
does it look like? Does it like fold the ring in half?
No, second molecule.
Oh, okay, I see.
And it would end up polymerizing in this case.
That makes sense.
So if I don't want it to attack there, really what I'm saying is that I need this position to be protected. Well, what do I have as a protecting group for my carbonyls?
You could use the glycol.
I think it is glycerol. I think you're right on that. We can use a protecting group. Now I no longer have that carbonyl, so that when I go through and make the Grignard can then go through and attack and be clean. So how did I make this structure? Well, if we worked all the way backwards, we had Mg. For those of you that love retrosynthesis, you'll notice that, am I really doing this in a retrosynthesis type fashion? No. You're not the only one that doesn't like doing retrosynthesis. Need to have the bromine so that it reacts. And actually, I can just get away with writing H3O plus to protonate the alcohol, because at the same time that it protonates the alcohol, what will it do? Will protonate, protonate, and deprotect. Kind of make sense? So when you look at somebody doing retrosynthesis and they're going beautifully backwards, the only reason they're going beautifully backwards is because they know the answer. Okay. Most cases it'll be kind of a mess. And I would argue even this looks pretty nice. Okay. Questions? So good call on pointing out the protection group. Appreciate that. And then no questions? Nothing at all?